So let us have a recap of the previous class. So in the last class, we discussed about the weightage of the engineering mathematics in the GATE examination. So as we have seen, it is 15 marks, 13 to 15 marks in the case of all the streams except computer science. And in the case of computer science, the weightage is around 8 marks. We have also seen the chapters that we are going to discuss in the curriculum of engineering mathematics. And then we started discussing about the first chapter, which is linear algebra. And we have seen that in the case of linear algebra, we'll be having two tools. One is matrices and the other is the vectors. So here we are going to learn initially about the matrices and followed by the vectors. Okay. So when we started discussing over the matrices, we have seen that representation of a matrix, how we can represent a matrix in terms of rows and columns, what is an order of the matrix, what happens if the number of rows is equal to number of columns, we call it as a square matrix. If it is equal to that of number of rows is equal to number of columns, we call it as a square matrix. If it is not equal, we call it as a rectangular matrix. We have seen some basic things. What is a row vector? What is a column vector? What is a diagonal matrix? What is a diagonal matrix? What is a scalar matrix? What is identity matrix? So these are the basic things that we have learned. Followed up with the operations. We came to know that when we want to perform the operations like addition and subtraction, we have to ensure that the order of the matrices upon which we are doing the addition or subtraction, both are going to be equal. If you are having something called as a 3x2 matrix and the other is a 2x3 matrix, we cannot do the addition or subtraction. Next, we came to the multiplication by a scalar. So whenever you are going to multiply a matrix with that of a scalar, then each and every element of the matrix is going to be multiplied by the same scalar. Then we came to the multiplication of the matrices. So when we see the multiplication of matrices, we have a condition. The condition is that the number of columns of the first matrix should be equal to the number of rows of the second matrix. So this is a very important condition for the matrix multiplication. And as we have did the matrix multiplication, we have seen two conditions. One is for total number of scalar multiplications and the total number of scalar additions. So total number of scalar multiplications in the case of two matrices, one of m cross n, the other of n cross q, is going to be m cross q, which is going to be the resultant order of the matrix multiplied by n. And similarly, for the case of the additions, it's going to be m cross q multiplied by n minus 1. And in the last class, we have done the problems which were mostly based on the multiplications, the total number of scalar multiplications, what is the minimum scalar multiplication which is required to perform the matrix multiplication in a given order. So these are the things that we have discussed in the last class. So in the current class, we're going to discuss about the other types of matrices based on the operation called as transpose. So what happens when we do the transpose on the matrix? So after doing the transpose, then we are going to do we are going to see the different types of matrices like symmetric matrix, skew symmetric matrix, orthogonal matrix. And after completing this concept, we will see the concept of determinant. If time permits, then we will also see the concepts of what is cofactor, what is minor, what is adjoint, what is inverse. Okay, so this is what we are going to do in today's class. Hope all of you are feeling comfortable in the class. If not, please let me know. And one more instruction that I have given in the last class, I want to repeat once again that whenever the content flow is going on, then we have to ensure that you are writing what all doubts come to your mind. Please write on a piece of paper, and when the doubt solving part is going to start, which we can have in the middle of the session after when we have either completed the break or just 10 minutes before the break, we can have the doubt solving part. So session break is going to be around 7:30. So after again at the completion of the lecture around 8:45 or 8:15, we will have the second session of the doubt solving. This is how we are going to do it. So the reason why I told that please keep your doubts with you is that so that it's not going to hamper the flow of the class, which is very, very important. Please write on the question on secondary screen. So it is already given in the question that we can write the matrix A as the low L and U, where L is the lower triangular matrix. I think we have discussed in the last class what is the lower triangular matrix. All the elements above the principal diagonal, if they are going to be equal to 0, we call them as the lower triangular matrix, otherwise it's a upper triangular matrix. Okay, if all the elements below the principal diagonal are equal to 0, we can call it as a upper triangular matrix. So now you are having L and U, right? So already A is given to us. What is A? A is equal to 2, 1, 4, minus 1. Yes or no? This is what the A is given. The best way to solve this problem is using the option elimination. There is another method also, but let us do this first of all using the option elimination method, right? So let us check the first option. The first option given is that 1, 0, 4, 1 multiplied by 2, 1, 0, minus 1, which equals what? 2, 1, 8. But we want 4, so therefore this cannot be the answer. Option B, let us go for that. 2, 0, 4, minus 1 followed by 1, 1, 0, 1. 2 here, 2 here. So I think even we can eliminate this part. C, 1, 0, 4, 1 multiplied by 2, 1, 0, minus 1, which gives 2 and 1 and 8. In fact, if you observe, option A and option C are same. I think there is some plus or minus difference. And then the last one, which is 2, 0, 4, minus 3, 1.501. So you have 2 first, and then it is 1, and then it is 4, and then it is minus 1. And this is the matrix A. So it means that the answer is option D. Clear? So the conventional method is something like this, which will definitely take some time to solve it. We can write the matrix A, we can decompose the matrix A in terms of the product of the lower triangular matrix and the upper triangular matrix, where the lower triangular matrix will be something like this: A, B, C, 0. And the upper triangular matrix, if I take A and B here, I will take 1, 1. And of course, because it's an upper triangular matrix, you will have a D here and the value is 0 here. This is one way of writing it, or we can also write something like this: 1, 1 over here, 0, A. Okay, this A and this A are not same, these are different. If you want, I can write in a different way also. Let me extend this. It can be E here, and then F, G, H, and 0. So these are the two ways of writing it, okay? Either you can ensure that in the case of the lower triangular matrix, you can have A, B, which are of course generally are not going to be equal to 1, or you can ensure that if you are having 1, 1 here. But if you are having 1, 1 in the lower triangular matrix upon the principal diagonal, then you have to ensure that here it is not 1, 1. So if I don't take 1, 1 here in the lower triangular matrix, then I will take in the upper triangular matrix, I will be taking the values as 1 and 1. Okay, so now we can write this as equal to the top. What is the product equal to? A, AD, C, and then CD plus B. Then what you will do? You will compare with the top the value of A. So whatever A is given, which is 2, 1, 4, minus 1, and then you will compute the values of A, B, C, D. Okay, so then this is equal to the of F, H, EF, EH plus G. And then you will find the values again. You will equate to the same matrix and then you will find the values of EF, G, H. Okay, this is the method that we are following because we want it to be equal to the of the matrix, whereas you are writing it in the form of the lower and upper triangular. If you don't take the values of 1 and 1, then you cannot equate it. The best way to equate it is that you have to consider the values of 1 and 1 in either the upper triangular matrix or in the lower triangular matrix. In the first one, we have taken the principal diagonal to be 1, 1 for the upper triangular matrix. In the case of the second one, we have taken in the lower triangular matrix the values of 1 and 1 in the principal diagonal. See, you will be getting two different answers of the values of A, B, C, D in both the cases. So what we are doing here, there are two ways of doing it. You can either consider, our objective is that we are going to write the matrix in the form of the lower and upper triangular matrices. That is our objective. So if that is the case, then what we are going to do, I will take A, B, C, 0, which is nothing but the lower triangular matrix. If I take A and B, which are not necessarily 1, then I have to ensure that the upper triangular matrix principal diagonal is going to be 1 and 1. And the remaining one element is going to be D. Or I will just take the opposite of it. I will take 1 and 1 here, and here it is going to be E, and here it is 0. And here, because I have already taken 1 and 1, here it should not be 1s. Here it should be any other values. As I have taken here, F, G, H. And I am going to equate to the actual matrix and I will find the values of A, B, C, D or E, F, G, H. The values of A, B, C, D and E, F, G, H are going to be different. So it means that there are two possible ways of writing it in the form of LU. Even in the case of the 3 by 3 matrix, we will follow the similar method. If you are asking about the conventional method, we will follow the similar method. We will ensure that fundamentally it is going to be a lower triangular matrix. It means that the elements above the principal diagonal are going to be equal to zeros in the case of a lower triangular matrix. And remaining elements are going to be something like A, B, C, D, E, F, G. And if you have taken the principal diagonal elements not 1, then you have to ensure that in the case of the upper triangular matrix, you are going to take the principal diagonal values as 1. And it is applicable not only in the case of 2 by 2, it is even applicable in the case of 3 by 3. But as you know that if the question is asked on 3 by 3, then it's going to be lengthier. So therefore in the gate, if at all the question asked about the LU decomposition, it will mostly come in the concept of 2 by 2 matrices only. That is why I told Vinaya that we are taking 1 and 1 so that we are able to equate to the value of A. Otherwise it's going to be quite complicated. In fact, you might be having more number of unknowns if you are not taking the values of 1 and 1. We should also take that into consideration. If you are having lesser equations and more number of unknowns, probably it is not possible to solve it. We will be having more number of solutions. Yes, the best possible method is going to be the optional elimination without any doubt. It's an easier method to get the answer. Next, please write down transpose of the matrix. Transpose of the matrix. Transpose of the matrix. Transpose of the matrix. So what happens if you are applying the transpose on the matrix? Is there any condition like if you wanted to apply the transpose, it should be a square matrix? Will there be any condition like that? That if at all we want to apply the transpose, it should be a square matrix? No, there is no condition like that, right? There is no condition like if at all we have to apply the transpose, it should be a square matrix. Simply, what the transpose does is that it tries to convert the rows into columns and columns into row. That is nothing but transpose. For example, if I take the matrix A, which is Aij, A suffix ij, m cross n, then A transpose is going to be equal to Aj n cross m. It means that it is going to interchange the rows and columns. It is going to interchange the rows and columns. So if I have a matrix, a 2 by 2 matrix, 1, 2, 3, 4, if this is my matrix A, then A transpose is going to be equal to the of 1, 3, 2, 4. This will be the value of A transpose. Okay. So if I have another example, a 3 by 3 matrix, A is going to be equal to the of 3, 4, 5, 1, minus 2, minus 9, minus 2, 4, 3, minus 2, 4, minus 3. Now this is a 3 by 3 matrix, isn't it? So if this is a 3 by 3 matrix, the transpose of this matrix, is going to be equal to the of, the rows are going to be converted into column and columns into rows. So it becomes 3, 1, minus 2, 4, minus 2, 4, 5, minus 3, minus 9. 5, minus 9, minus 3. This is the transpose of the matrix. So the rows and columns are getting interchanged here. So there will be some simple properties. Again, it is not important in the examination point of view to remember it. And it's quite logical. If I do A transpose whole transpose, it means you are converting rows into columns and columns into rows. Again you are applying transpose. Then again the columns becomes rows and rows into columns. It means that logically it should be the same matrix that we already had. So if I do A plus B, if I'm adding two matrices A and B, so what is the condition for adding two matrices? If at all I wanted to add two matrices, I have to ensure that both of them are of same order. So A plus B whole transpose is going to be equal to A transpose plus B transpose. And if I take a product of the matrices A and B, whole transpose is going to be equal to the of B transpose A transpose. So these are the properties of the transpose of the matrix. Please take the question on secondary screen. So the matrix J has been given and there is one more matrix which is K. Can you please tell me whether it is a row vector or a column vector which is given here? The K. So it is a column vector because it is having only one column. It is having only one column, so therefore it's a column vector. Now K transpose is going to be 1, 2, minus 1. Now J, which is 3, 2, 1, 2, 4, 2, 1, 2, 6. And then comes 1, 2, minus 1. So 3 by 3 matrix, 3 cross 3 matrix, and you are having 3 cross 1 matrix. Let me multiply these two first of all. In that case, I'm going to have a 3 cross 1 matrix as a result. So it is going to be 3 plus 4 minus 1. So it is 6. Right? So then you have 2 plus 8 minus 2. It will be 8. And then you have 1 plus 4 which is 5 minus 6 which is minus 1. And then it's 1, 2 minus 1. It's going to be equal to the of. So this is a 1 cross 3 matrix. So you will have the result as 1 cross 1 which is 6 plus 16 plus 1 which is 23. It is a single number. So the answer is 23. So two matrices are given here. It's again a very simple question. So B is given 3, 7, 8, 4. So when I calculate the transpose of it, the transpose of B is going to be B transpose, which is 3, 8, 7, 4. And here it is 1, 5, 6, 2. So we will have 3 plus 35, which is 38. And then you have 8 plus 20, it is 28. And then you have 18 plus 14, which is 32. And then you have 48 plus 8, 56. So 38, 28, 32, 56. It's the option A. There is a quiz question for you. Please read it carefully and tell me the answer. A is clearly given, it is going to be a 3 cross 4 matrix. But we can assume that B is going to have m cross n, where we can find the values of m and n. Now, if A transpose B is defined, it means that the multiplication of A transpose and B is possible. That is the meaning of it, isn't it? So, A transpose is going to be 4 cross 3, and here you are having m cross n. It means these values are same. M is going to be equal to the top of 3. So, the resultant is going to be 4 cross n. And even B A transpose is possible. It means that the B is going to be m cross n and A transpose is going to be 4 cross 3. It means the value of n should be equal to the top 4 if at all B into A transpose is defined. Clear? So therefore, the value of m is 3 and the value of n is 4. It's going to be a 3 cross 4 matrix. This will be the order of B. I think it's very clear. So it is already given, and here we are taking the m cross n. So A transpose B, it means that you are taking the transpose of this, which is 4 cross 3, and whereas you are having m cross n here, and we know whenever the multiplication should be defined, it means that the number of columns of the first matrix should be equal to the number of rows of the second matrix. So the value of m is equal to the top 3 because these two are same, then only it is possible for A transpose B to be defined. And similarly, B transpose A to be defined, the value of n should be equal to 4. It means that you are going to have a matrix which is 3 cross 4. Now you have a class of matrices that sometimes what happens, the transpose of the matrix will be equal to the matrix itself. It means, so whenever you are applying the transpose of the matrix, it will be the matrix itself. Such sort of matrices are what we call as the symmetric matrices. Such sort of matrices are what we call as the symmetric matrices. So whenever the transpose of the matrix is going to be equal to the matrix itself. Now how is it possible? Let us consider that A is going to have Aij m cross n. Now what happens? The transpose of A will be equal to Aj n cross m. Now if I say 1 and 2 are same, 1 and 2 are equal, that is the meaning of a symmetric matrix. That is the meaning of a symmetric matrix. It means that the value of Aj n cross m should be equal to Aij m cross n. It means because you are equating two matrices, say it is possible to equate two matrices only when their orders are same. If the orders of the matrices are different, then it is not possible to equate two matrices. So to equate matrices, the essential condition is that the order of both the matrices should be what? Should be same. Order of both the matrices should be same. It means that the value of m should be equal to n. If m is equal to n, we know that whenever the number of rows is equal to number of columns, it's going to be a square matrix. So the first condition for a symmetric matrix is that it should be a square matrix. You cannot have a non-square matrix, which is a rectangular matrix, satisfying the symmetric matrix. So the number of rows should be equal to number of columns. So the value of, it should be a square matrix. This is the first condition. Now, once it is accepted it's a square matrix, then you should also satisfy the condition that Aj should be equal to Aij. Aj should be equal to Aij. It means what? Aj is equal to Aij means that if I take the values of A12, it should be equal to A21. If I take the values of A31, it should be equal to A13. If I take the values of A23, it should be equal to A32. If I take both I and j are same, which are principal diagonal elements, A11 is equal to A11, A22 is equal to A22, A33 is equal to A33. It means that there is no condition actually for principal diagonal matrix. It can be any values. So it means that you can have any values. You can have any possible values in the principal diagonal. Now if I write x here, what is x here? This is nothing but A12. First row, second column. Then you should have the same element at A21, which comes here. Similarly, if I have an element y here, which is nothing but A13, the first row and third column, then third row and first column should also be the same element. If I have Z here, which is nothing but second row, third column, then third row, second column should also be the same number. So this matrix automatically satisfies the symmetric matrix. So whenever you are having a matrix like this, it will automatically satisfy, it's a symmetric matrix. So do we have any condition on principal diagonal elements? Do we have any condition on the principal diagonal elements? We don't have any condition on the principal diagonal elements. It can be any possible values. Now, you should be careful when you are writing these values. If I write 0 here, it should be a 0 here. If I write 2 here, it should be a 2 here. If I write 4 here, it should be a 4. This is how we can directly construct a symmetric matrix. This is how we can directly construct the symmetric matrix. This is what we call as a symmetric matrix. Now, there is a second type of matrix, which is A transpose is equal to minus A. A transpose is equal to minus A. It means that when you apply the transpose, it will be the matrix itself multiplied by minus sign. Multiplied by minus sign. Such type of matrix is what we call as a skew symmetric matrix. It is what we call as a skew symmetric matrix. So whenever the transpose of the matrix is equal to the same matrix with a minus sign, such matrix is what we call as a skew symmetric matrix. That is what we call as a skew symmetric matrix. So again, if I take these two matrices as 1 and 2, if I'm equating it, then the value of 1 should be equal to minus 2. Then the value of 1 should be equal to minus 2. It means that there is a minus sign which comes here, but still we are equating two matrices. It means that here also the value of m should be equal to 1. M should be equal to n. Again, it should be a square matrix. The only difference is that Aji will be equal to minus Aij. Okay, so because you are equating, the moment you are equating, it should always satisfy the order of the matrix should be the same, right? So therefore, it should again be a square matrix, and the remaining values Aji should be equal to minus Aij, because once these two are same, it means that Aji should be equal to minus Aij. Now what happens? A12 will be equal to minus A21, A31 will be equal to that of A minus 13, A23 should be equal to minus A32. Now this is how it is going to be in the case of a skew symmetric matrix. This is how it is going to be in the case of a skew symmetric matrix. Sometimes, instead of saying it as a skew symmetric matrix, we can also call it as an anti, not onti. It is anti. We can call it as a anti-symmetric matrix. We can call the same matrix as a anti-symmetric matrix. Now, how to reconstruct? So, we have talked about the off-diagonal elements. Off-diagonal means those elements which are not the part of the principal diagonal are what we call as the off-diagonal elements. Now, when it comes to the remaining elements, what are they? The principal diagonal elements. Then what is the condition? A11 is equal to minus A11, A22 is equal to minus A22, A33 is equal to minus A33. Have you ever seen a number being equal to minus of that number? If I say A11 is equal to minus A11, have you ever seen a number where the minus of the number is equal to the same number? It is possible only in the case of 0, because we know whether it is plus 0 or minus 0, it means the same thing. Whether it is plus 0 or minus 0, it is going to mean the same thing. So therefore it means that all our principal diagonal elements should be equal to zeros. All the principal diagonal elements is equal to zeros. So A11 is equal to A22 is equal to A33 is equal to so on. It should be equal to zeros. That is how you are going to have a skew symmetric matrix. So the essential condition in the case of a skew symmetric matrix here is that we do have a condition for a principal diagonal. So what is that condition? The principal diagonal elements are going to be equal to zeros. The principal diagonal elements are going to be equal to what? They are going to be equal to the top zeros. Now what happens in the case of these elements? If I have a x here, there will be a minus x here. If I have a12 value as x, then a21 should be equal to minus x. If I have y here, there will be a minus y. If I have z here, there will be a minus z. So this is how a skew symmetric matrix is going to be. This is how a skew symmetric matrix is going to be. Now when it comes to this one, I can erase this principal diagonal elements and replace them with the top zeros. I'm sorry. Is this clear? Now we will also have the class of matrices. We will also have the class of matrices where the transpose of the matrix will not be equal to A, neither it will be equal to minus A. It is also possible that we have a matrix where the transpose is not equal to that of A. See, if the transpose equal to the same matrix, we call it as symmetric. If the transpose is equal to minus of that matrix, we call it as skew symmetric. It is also possible to have the matrices which are not going to satisfy either of these conditions. In such a case, we call it as non-symmetric matrix. What we call it as? We call it as a non-symmetric matrix. We call it as a non-symmetric matrix. Clear or not? We call it as a non-symmetric matrix. A matrix which is neither symmetric nor skew symmetric is what we call as a non-symmetric matrix. Please take this example that you have a matrix A, and clearly you can see that the matrix is not going to be symmetric, it is not going to be skew symmetric, because if you look at the matrix itself, now you are in a position to say whether it is going to be symmetric or skew symmetric or not. In the case of skew symmetric, very first thing is that all the principal diagonal elements are going to be 0. A12 is equal to minus A21, A13 is equal to minus A31, A23 is equal to minus A32. That is how you are going to have a skew symmetric matrix. When it comes to the symmetric matrix, then you will have a principal diagonal element. See, these matrices, what is the significance of symmetric and skew symmetric? Because there are some advantages, okay? When we learn about the concepts of eigenvalues and eigenvectors, probably we will understand it better, okay? That we have a relation between the symmetric matrix and how the properties of the eigenvalues and eigenvectors are going to be. And same with that of the skew symmetric matrix. And let me also tell you, after studying the concept of determinant, you will see that if at all we are having a square matrix which is skew symmetric and of odd order means it's going to be 3 by 3, 5 by 5, 7 by 7. So directly the determinant is going to be equal to the top 0. So so there is a query to repeat the determinant part. Actually, there was a question from a student, what is an advantage or the physical significance of having a skew symmetric? It is not like that. Whatever mathematics here we're trying to study is that we can relate with the other concepts. Okay. So one of the concept is that the concept of the eigenvalues and eigenvectors, where we are going to effectively use the concept of symmetric and skew symmetric. And also sometimes the determinant will be given. It is asked to find the determinant, and provided if you are having a skew symmetric matrix of odd order means a 3 by 3 or a 5 by 5 or a 7 by 7, directly the determinant is going to be equal to the top 0. Okay, after studying the concept of determinant, you can verify with any example that you're going to consider. See here, first thing is that, okay, the general observation here in this case is that it is neither a symmetric matrix nor it is a skew symmetric matrix. Okay. So to an extent we studied about symmetric and skew symmetric. This matrix is not satisfying either of them. Okay, so the question is different here. We have to find the values of A transpose. The transpose of the matrix will be what? 1, 5, 3. 2, minus 1, 1. And minus 4, 2, 6. The second part is that B, which is A plus A transpose. What is A? 1, 2, minus 1. 1, 2, minus 4. 5, minus 1, 2. 3, 1, 6. Plus 1, 5, 3. 2, minus 1, 1. Minus 4, 2, 6. So 1 plus 1 is 2. Here we have 7. And then we have minus 1. And then we have 7 again. Then we have minus 2, and then we have 3, and then we have minus 1, and then we have 3, and then we have 12. Now you observe what is happening here. We see that this element and this element are same. We also see that these two are same, and even these two are same. What does it imply? It implies that A plus A transpose is going to be a symmetric. Very good. A plus A transpose is going to be a symmetric matrix. it means that A plus A transpose is symmetric in nature. Then we'll come to the top A minus A transpose. So 1 minus 1 is 0, minus 3, minus 7, and then you have 3, 0, and then it is 1, and then it is minus 1. So the presence of zeros, yes, here it is 7. Sorry. Right. So the presence of zeros in the principal diagonal elements will give us an indication that the matrix is going to be what? The matrix is going to be a skew symmetric matrix. Let us see whether these elements are having negation or not. We have 3 here, there is a minus 3, there is a 7 here, there is a minus 7, there is a minus 1 here, there is a 1. So it means that it is a skew symmetric matrix. It is a skew symmetric matrix. It is a skew symmetric matrix. Now let us go for A transpose A. The multiplication of A transpose with of A. Let us multiply A transpose and A. A multiplied by A transpose. So here it is 1 plus 4 plus 16. It's going to be 21 here. And then it is going to be 5 minus 2 minus 8. It's going to be minus 5. And then we are going to have 3 plus 2 minus 24. So it is going to be minus 19 here. And then I'll have 5 minus 2 minus 8. It's going to be minus 5. And then I'm going to have 25 plus 1 plus 4. It is 30 here. And then I'm going to have 15 minus 1 plus 12. So what is this number? It's going to be 26. And the last one, 3 plus 2 minus 24. So it is minus 19. And then I'm going to have 15 minus 1 plus 12, which is 26. And the last one is 9 plus 1 plus 36, which is going to be 45 plus 1, which is 46. So you can check with it of E, which is A transpose multiplied by A. It will also come to be a symmetric matrix, right? So one observation we can write is that if the matrix A is non-symmetric, sometimes we can also call it as asymmetric, a symmetric matrix. Okay? If A is a non-symmetric or asymmetric matrix, in such a case, A plus A transpose will always be symmetric. A minus A transpose will be skew symmetric. A multiplied by A transpose, comma, A transpose multiplied by A are also going to be symmetric. And then we try to write a non-symmetric matrix as a summation of the symmetric component plus the skew symmetric component, where the symmetric component is A plus A transpose and the skew symmetric component is A minus A transpose. So if you try to relate, because we came to know that if you add them it's going to be symmetric, if you subtract them it's going to be skew symmetric. So I'm trying to write the matrix in terms of symmetric and skew symmetric. Now symmetric is going to be A plus A transpose, skew symmetric is going to be A minus A transpose. If I try to equate it, then I'll have at the right hand side it's going to be 2A, whereas in the left hand side it's going to be A. I cannot equate A and 2A, so what I'll do, I'll better divide it by 2. So whenever you have a matrix which is non-symmetric in nature, we can still write it as an addition of symmetric and skew symmetric components. Symmetric component is going to be A plus A transpose by 2 and the skew symmetric component is going to be A minus A transpose by 2. So we are dividing it by 2 for the simple reason that we cannot equate A and 2A, right? Can we equate A and 2A? Not possible. So we have to ensure that even this side we are having A. So only way of doing is that you are going to divide it by 2. Right? Symmetry is a very important concept for the fact that if you are having symmetry in your elements, whatever data you are having, if you are having symmetry, then it becomes easy to process the data. If it is not having symmetry, then it is difficult to process the data. So sometimes even if it is not having symmetry, we try to represent it as a summation of symmetric and skew symmetric part, which are both are having symmetry in it. In a way, even symmetric and skew symmetric both are having symmetry inside it. One is applying transpose, you are having A itself, the other you are having minus A. I think this is what we have discussed. For a symmetric matrix, it must satisfy Aij is equal to Aj, which is absolutely correct. Second statement is not correct because it is not required to satisfy Aij is equal to 0 for I is equal to j in the case of a symmetric matrix. Third one, in the case of a skew symmetric, Aij should be equal to minus Aj, which is correct. Even the fourth statement is correct, that is Aij is equal to 0 for I is equal to j. So it means that 1, 3 and 4 are true. So what is the matrix which is both symmetric and skew symmetric? Absolutely correct, it is nothing but a null matrix. Null matrix means if all the elements of the matrix is going to be equal to 0, we call such a matrix as a null matrix.